Okay, guys, I am going to recapture what was covered in class today with the grad assistant. I was afraid there might be a few things that you were still a little confused about. So let me go through this and see if this will help you better understand the material. So we're talking about rational functions, and a rational function comes in the form. Ooh, I need to get to my pen. I need to move this down here. All right, I got to stop. Okay, guys, I'm going to do a quick wrap up of what was covered in class today. I thought there may be a couple of questions you had regarding the lecture, and so here I go with a quick recap. The functions we're dealing with are rational functions, and rational functions are fractions. They come in a form, and the form is called, or looks like this, and P and Q are just polynomials that we worked with in chapter 3. So we're going to look at functions in this form. Some things we need to know how to find when we have a function in this form would be the domain. And when working with the domains and we have a function in fraction form, we cannot have division by 0. So to find the domain, we have to find the values that make the denominator 0. So all we do is set the denominator to 0 and solve. So in this case, x minus 2 equals 0 tells me x is 2, and for my domain, it's all real numbers, but x cannot equal 2. For this next one, to find the domain, I'm going to set the denominator equal to 0. I'm going to solve it, square root both sides, and so I'll get x equal plus or minus 2. Square root of 4 is 2. Those are the values I have to exclude, so my domain would be all real numbers, but x can't be positive and negative 2. Next one, I set my denominator to 0 and solve it. When I go to solve this, I bring the 9 over, it becomes a negative 9. And when I square root both sides, I have an issue because I get a plus or minus 3i. And since we're only working in the real number system, this domain is not going to have a restriction because there's no value, there's no real number that we can put in place for x that would give us division by 0. So there is no restriction, it's all real numbers. Now the interesting thing is the values you found for the domain restrictions on these problems, those restrictions are also where our vertical asymptotes occur. So x cannot equal those values. At those values, we have what we call a vertical asymptote, which is drawn on your graph as a vertical line. As you see here, vertical asymptotes are drawn as vertical lines. Your graph cannot touch or cross over that vertical line because that's where the denominator is 0. So when we start graphing our functions and it has asymptotes, we need to mark those asymptotes at a dotted line and never cross over it. What is going to happen is that your graph is going to approach those vertical asymptotes on either side, either going up or going down. So over here, I may have actually, let's look at this one. It has a vertical asymptote at 2. If I graphed that function, which is x plus 4 over x minus 2, oops, lost that. I'll see these two curves I'll see these two curves and notice that they're kind of going up and down to infinity. That occurs at that vertical asymptote. So your graph will show you what's occurring at those asymptotes. So we have the graph approaching that asymptote, never crossing over it. So vertical asymptotes occur at what makes the denominator 0. They're an equation, so we write them as x equal. And when we're graphing, the graph approaches but never crosses these. So again, the vertical asymptotes will occur at the zeros of the denominator, whatever makes that denominator 0. So we found the domain for these problems earlier, so the vertical asymptote will just be at those domain restrictions. For the first one, x equal 2. For the next one, x equal 2 and x equal negative 2. It'll have 2 vertical asymptotes. This one had no restriction, which means it's not going to have any vertical asymptotes. Okay, how to find x and y intercepts? Well, here's how we're going to do it. To find x-intercepts, we let all the x's be 0 and just do some reducing. That was y-intercepts. To find y-intercepts, we let all the x's be 0 and reduce that value. To find x-intercepts, the only thing we need to do is find where the numerator is 0. So all we're going to do is set the numerator equals 0 and solve to find that x-intercept. So let's work on that. So for the y-intercept, I'm going to put a 0 everywhere. I have an x, so 0 plus 4, 0 minus 2, which gives me 4 over negative 2, which is negative 2. There's my y-intercept. The x-intercept comes from setting the numerator equals 0 and solving. X equal negative 4. There's my x-intercept. Coming over here, the y-intercept, we're going to put 0 everywhere we have an x. That reduces to 0 over negative 4, which is 0. So the y-intercept is 0. And for the x-intercept, we'll take the numerator, set him to 0, and solve for x. So I would divide by 2, x squared equals 0, and square root both sides, so I basically get x equals 0. So the y-intercept and the x-intercept for this one happens to be the same number, 0. Okay, let's look at the last one. Y-intercept, we let all the x's be 0, so 0 minus 3, 0 squared plus 9 gives me negative 3 over 9, which is a negative 1/3. There's my y-intercept. X-intercept, you remember what you do? Set the numerator to 0 and solve it. So this gives me x equal 3. There's my x-intercept. There is my y-intercept. X-intercept, y-intercept. We'll need those points when we're graphing our function. Last asymptote, excuse me, the last item we need in our list is how to find a vertical asymptote. Now keep in mind your graph may cross vertical asymptotes, but it will never cross your horizontal asymptote. Excuse me, had that backwards. Your graph will never cross a vertical asymptote. It may cross the horizontal asymptote, and I can't get my pen to work. Come on. Come on, pen. Come on, cutie. Well, we'll just have to be just a little bit slow. All right, well, whatever. I can't get it to work right now. But just keep in mind, you can cross over those horizontal asymptotes. So here is the theorem we have to use when finding horizontal asymptotes. We compare the degrees, and we are going to look at the degree of our leading terms. One pen. Let me pair it up. Maybe it's not paired. Let's try this again. Okay, so maybe I have to use this. Where is it? Put him. See if he'll work right here. Let me pause. All right, got that pen to work. So for the horizontal asymptote theorem, we compare the leading term at the top and the leading term at the bottom, and we look specifically at the exponents. And we call the top exponent n and the bottom exponent m. And we compare them to see if they're equal, one's larger, one's smaller, to determine our horizontal asymptote. And it's the highest degree. Whatever term, you look at the highest degree term on the top. And the highest degree term on the bottom. So those are the two guys you mark. And then here's the situation. If the degree, that exponent on the numerator's term, is less than the degree of the exponent on the denominator, that means n is less than m, then the horizontal asymptote is always y equals 0. If the degree of the numerator is equal to the degree of the denominator, n is equal to m, then the horizontal asymptote is going to be the line y equal the two coefficients in front divided by each other, a over b. And final case, if n is greater than m, that means the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Okay, so we now have all the skills necessary to get information about a rational function and then graph some rational functions. So let's take a look. Now let's quickly find some horizontals. So check out the degree. The degree at the top is 1. The degree at the top is 1. So n is equal to m. And when that's the case, you take the equation y equal to the coefficient of 1 divided by the coefficient of 1, which is just y equal 1. The next one, let's look at the degree. The degree over here is 2. The degree over here is 2. Since n is equal to m, it's going to be the line y equal to a over b. And in this case, it's 2 over 1. So it's y equal 2. There's your horizontal asymptote at 2. Okay, this guy, the degree at the top is 1. The degree at the bottom is 2. So the top is less than the bottom. So that's our line y equals 0. We go back to the theorem. And when the top degree, 3, is greater than the bottom degree, in this case 2, top is greater than the